Okay, so in this video, we're going to be looking at some questions involving the continuity of function on metric spaces. So just to recap, okay, so there are many different ways we could define the continuity of functions. It turns out for this particular question, the definition that is the easiest to use is the topological definition of continuity, and that is if f is a continuous function on a topological space, then it pulls back open sets to open sets. So recall, we could say that f, let's just say, so even though it's going from x to r, I'll just go x to y, is continuous on x if the pre-image of E is open in X whenever E is an open subset of Y. Okay, and the diagram for this looks like, let me see if I can draw it. Here's X, there's Y, and we have a function f from X to Y. So we say f is continuous on X if, so it works so it doesn't take open sets in X to open sets in Y, but rather it does the reverse of that. So what I'm saying is, if we have an open subset E in Y, then the pre-image of this guy, or the pullback, so this is F in, so I shouldn't say F inverse, this is the pre-image of V because this is not the inverse. So let me say this is the pre-image. Okay, that's the pre-image, not the inverse. Then the pre-image of E is this set here. And this is F pre-image of E. So when this is open, Y, this guy will be open in X. Okay, so it pulls back the open sets of Y into the open sets, into an open set in X. And let me also just quickly remind you what exactly is this pre-image. Okay, because it's not the inverse, it only has an inverse if the function f is bijective, but in general, continuous functions do not all have to be bijective. So f to the minus 1e, the pre-image of E is just all the points in the domain X, in the domain X, such that when you apply F to it, you end up in E. So it's just all the points in the domain that map to the set E. That's what the pre-image is. Okay, and I claim that this is going to be useful to show these two results. So in this case, our set Y happens to be the real numbers, okay? And they gave us here that you may assume R has the usual metric. So R has the usual modulus on it. And if we're dealing with the real numbers with the usual metric, then it has the usual topology. So the open balls are just open intervals, and the open sets are just arbitrary unions of open intervals. So that's the topology we're dealing with in R. Now X, we don't know. X could be any set. So we're given E1, and E1, okay, so we're down here. E1, we're given that the set E1 is the set of all elements in X such that when you apply F to it, this is equal to 0, okay? Another way of writing this is it's a set of points in the domain X such that when you apply X to it, you end up in this set, singleton 0, okay? That's the same thing. So the reason why I'm doing that is because I want it to look like this definition of the pre-image. Because now I could see that E1 is simply the pre-image of this set, singleton 0. It's just the pre-image of the singleton set. It's everything in X that maps onto 0 in the real numbers, okay? And since I know that, okay, so I didn't say it here, but also very useful. Let me see if I can move everything down a bit. Because I want to write this definition, but in terms of the closed sets. So I have recalled that F is continuous on X if it pulls back open sets in X. Oh, sorry, open sets in Y to open sets in X. Another equivalent way, so we could reformulate this in terms of the closed sets. This is equivalent to saying that F goes from X to Y is continuous on X if, so I don't want to use E, let me use F. Okay, let me not use F because I already have the letter F, but usually F is used for closed sets. Let me use G then. F, the pre-image of G is closed. So I'm rewriting the same definition, but with respect to the closed sets. So it not only does it pull back open sets in Y to open sets in X, but it also pulls back closed sets in Y to closed set in X. So if the pre-image of G is closed in X, whenever G is a closed subset of Y. Okay, so not only does it pull back open sets to open set, it also pulls back closed sets to closed sets. So let me also put that here, open in Y or close in Y, and it pulls it back to something that is closed in X. Right? Okay, good. So now we have everything we need because this set E1, notice I could write it as the pre-image of singleton 0. Now singleton 0 is a closed set in R with the usual topology, with the usual metric. So this is the pre-image of a closed set, but I know F is continuous, right? So this is the pre-image of singleton 0. And now, so we could maybe write something even more general. Every singleton set in every singleton set is closed in. It's closed in R. Okay, and that's of course with respect to the usual metric or the usual topology. Since F is continuous, then it pulls back closed sets to closed sets. So E1 is a closed set. Okay, because singleton 0 is a closed set, so the pre-image of it will also be a closed set. Now, what is the pre-image of singleton 0? It's E1. So E1 is closed. Okay, or you could say closed n, right? So that's the first one. E1 is a closed subset of X. Now for E2 and E3, it's a similar thing we're going to be doing. So E2, we are given as the set of elements in the domain X such that f of X is bigger than or equal to 0. Okay, now again, the strategy is I want to rewrite this set in terms of the pre-image of something. So this set is the same as simply saying that f of X, instead of saying f of X is bigger than or equal to 0, I could just say f of X belongs to this interval. Okay, that's the same thing as saying f of X is bigger than or equal to 0. So f of X belongs to this interval. But this is nothing but the pre-image of the set. 0 to infinity, but we include 0. Okay, that's just a pre-image of that set. So now I need to ask myself, is the half open interval 0 to infinity, is that an open set or a closed set in R? So now this set 0 to infinity is closed in R because since the complement of it, now remember a set is closed if and only if the complement is open. That's another way you could do things. So I claim that this set is closed in R since what is the complement of this set? And so the complement of this set is just this open interval. Is open in R. Right, so again, this set is closed. So just like before, since F is continuous, the pre-image of this closed set, right, which we know is another way of writing E2, is closed. The pre-image of closed sets is closed. Okay. And for E3, so E3 is again the set of all points in the domain such that f of X is less than, strictly less than 0. Okay. Now, again, we can write this in terms of, okay, we can write it in terms of the pre-image of some set. So this is just the set of elements in the domain X such that f of X belongs to, so if you are strictly less than 0, you are in minus infinity to 0. Okay, but if you look at what E2 is, E2 was a set of points where f of X is bigger than or equal to 0. And E3 is a set of points where f of X is strictly less than 0. So E3, if you look at it, E3 is just the complement of E2, right? This is just E2 complement. And I know from part 2 that E2 is closed. So if E2 is closed, the complement is open, right? So since E2 is closed, that we just showed that in part 2, then E3, which is just E2 complement, is open, and X. Okay, so in this question, we are given that X is a set of all continuous functions defined on the closed interval 0 to 1 with the suprema metric. And we want to show that these following functions are continuous on X. So we're given two functions. So psi defined on X, which is the continuous function from 0 to 1, is a mapping from X into R. So psi, you could think of it, it eats a continuous function and it gives you a number. So essentially what this psi is doing, if you look at it, how is it taking a function and giving you a number? It's just integrating whatever function you give it. It's just integrating it between 0 and 1. And of course, that would give you a number. And phi, again, is a function from x to r, is defined by, so phi, just like psi, is eating a continuous function. But how is it giving you a number? So psi takes in the function, and in order to give you a number, all it's doing is it's just evaluating that function at a point. Okay, so it's just taking that function and it's just evaluating it at some point lambda, where lambda is some fixed value between 0 and 1. So we want to prove that these two functions are continuous. So we just need to recall what is the supremametric. So the supremametric, the infinity metric, is given by the infinity of f comma g. That is just equal. So what you do is you just take the supremum over all function values where you subtract them. So you work out what is f of t minus g of t, take the modulus of that for all t in the domain of f and g. So f and g are continuous functions on 0 to 1. So t ranges between 0 and 1. And you take the supremum of this set. Okay, so that's the supremametric. You can think of it, essentially what the supremametric is doing is it's measuring the largest distance between these two functions on this interval. So maybe I can give you a picture of that. So here's 0, here's 1, and let's just say, so they are continuous functions. Let's just say this guy here is g. Maybe this one does something like that. So maybe this one is f. So where is the distance between these two functions largest? So it's largest. Yeah. Okay. So this distance, that is what the infinity fg is going to give you. Is the largest distance between them. Right. Okay, so for this one, we're going to tackle it using the epsilon delta definition of continuity. So let's first tackle psi. So psi takes in a continuous function and gives us a real number. And how does it do it? It's going to take a continuous function and then it's going to integrate that continuous function between 0 and 1. Okay. So for all continuous functions, next. All right, so I want to show that psi is continuous. So let epsilon be bigger than 0 and take or choose delta, and I'm going to leave a space here because I'm not sure what the relationship between delta and epsilon will be, but we'll see later on. So I'm going to take some delta such that for the, so I don't know what x is, right? So x here, this is just any metric space xd, such that for the distance between these two functions, f and g, with respect to the x metric is less than delta. This implies I need to, okay, so in this case, the points, so we need to think of what are the points. The points, we're used to thinking about the points in the metric space as being numbers. In this case, the points in this metric space X are continuous functions. So this is d infinity. Okay, so in this case, the point in this space is d infinity, such that for whenever these 2 points are less than delta, so let me just write down what that is. What does it mean for these 2 points, f and g, to be within delta? So the distance in x was d infinity, right? So another way of writing this is, um, let me write them together. So such that for this guy, so you just write another way. So what does this mean? D of x is the supremum metric. So that means that the supremum of the modulus of f of t minus g of t, where t belongs to and close interval 0, 1. So whenever this number is less than delta, okay, this implies now I need to work out what the distance between the image of these points are. So I need to work out what is the distance between psi of f and psi of g. Now psi, the image of psi, so psi of f and psi of g, these are just numbers. So this space over here is just R with the usual metric, the modulus. So what is this distance equal to? Now remember in the improving continuity using the epsilon delta definition, I need to show somehow that this distance between the image psi of f minus psi of g with respect to this metric, it's the usual metric in this space, is less than epsilon. So let's see if we could do that. Okay, so by definition, what is psi of f? That's just the integral. Okay, psi of f is just the integral of f. And what is psi of g? Minus psi of g. Psi of g is just the integral of g from 0 to 1. Okay, so that's just by definition what psi of f and psi of g is. And of course, you know from the properties of integral, we can write this as the integral of f of t minus g of t dt. Okay. And I can move the modulus inside, so here will become less than or equal to the integral from 0 to 1 modulus f of t minus g of t dt. Okay, and I do this because the modulus of the integral of f is less than or equal to the integral of the modulus f, right? And this quantity that I'm now integrating, that quantity is always going to be less than or equal to the supremum of that quantity. Okay, so this guy is always going to be less than or equal to the supremum of it. I take again the supremum over all values between 0 and 1. Okay, et. Yeah, so technically I should change the letter here, right, to a different dummy variable instead of using t for both the integration and the supremum. So maybe I need to use s, right? So I'll take the supremum over s, and then I integrate it now with respect to t. Now the supremum of this value, that is just a number. So everything inside of this integral, that is just a fixed number. So you could move that number outside, right? So if you wanted to, this is just equal, or in this case, yeah, we don't even need to use that because look over here from start, that supremum is less than delta, right? So this guy is less than the integral from 0 to 1 of delta dt, and delta is fixed. Okay, so I can move delta outside, and the integral of 1 from 0 to 1 is just 1. So this guy is just equal to delta, but I need it to be less than some epsilon. So what do? I set delta equal epsilon. And now I could come back all the way to the top here and say take delta equal epsilon. Okay, so what do we show? We showed that for any epsilon you give me, I could find a delta. How do I find a delta? I set it equal to the epsilon you gave me, such that when the distance between these 2 points, F and G, and by distance I mean the supremum metric between these 2 points is less than this delta, the distance in terms of the modulus now between the image of these points with respect to psi is less than epsilon. In other words, so therefore psi is continuous. So therefore psi is continuous. I think in this case psi is uniformly continuous. So we actually prove something even stronger. Yeah, psi is a uniform continuous. Uniformly continuous, which means psi is continuous. Okay. And for the second one, we will do something similar. So for the second one, it was the point evaluation. So it was phi takes a continuous function, maps it to a real number defined by, how does it do it? Psi takes a continuous function, and all it does is it evaluates f at some value lambda for some fixed lambda in 0, 1. Okay, so it basically takes all these functions and just works out what the value is at this fixed point lambda. So again, we could employ the same sort of strategy, which is let epsilon be given, and I'm going to take delta, and I don't know what this delta will be, so I'll leave it empty, such that whenever the distance with respect to the metric x between these 2 points, F and G, now what was the metric in x? It was the infinity metric, the supremum metric. So that means that what is the supremum metric between F and G? It's just the difference between the function values, take the modulus of it, and what is the supremum over all values in the domain. Okay, so whenever this guy is less than delta, this implies I need to show that the corresponding image on the side, sorry, on the phi. This is phi, the other guy's side. So that the image on the phi of f minus phi of g, and now I am in R, so R has a usual metric, so that's the modulus. I need to show this guy is less than epsilon. Okay, so by definition, what is phi? Phi is the point evaluation at the value lambda. So this is f of lambda minus g of lambda. Okay. But remember, lambda is some value in 0 and 1. So this is just some value in this set. But this set, I'm taking the supremum over it. So this guy is obviously less than or equal to the supremum over all of these values. Okay, the modulus of f lambda minus g lambda just corresponds to one possible value in that set that I'm taking the supremum over. Okay. Okay, so this is less than or equal to the supremum over all these values. Now the supremum over all these values, I assumed was less than delta. Okay. So now I need to be less than epsilon. So I could set delta equal epsilon. Right? So again, therefore, phi is uniformly continuous, which means phi is continuous. Okay. You don't always have to go through uniformly continuous to prove that it's continuous, by the way. But in this case, because of how the functions were and they were defined, it was easier to just prove it's uniformly continuous. And from that, you could then conclude it is continuous.